Hello everyone, in this video we will be discussing the topics of light and electromagnetic spectrum. So why is light important in astronomy? Well, the reason why light is so important in astronomy is because it's one of the few ways in which astrophysicists can study astronomy. When we detect light from stars or planets, we are able to know the compounds or elements in which create that star or planet. So it's a very significant aspect of studying astronomy. So now let's head on over to the topics of light and electromagnetic spectrum. So what is light? The light that we see in our daily lives are sunlight, or sometimes colored lights from our living room, our bathroom, anything like that. If we actually shine sunlight, pretend the sun is over here, we shine this light through a prism, and this is made out of glass, we're actually able to see all types of colors. So starting from red, orange, yellow, green, blue, indigo, and violet. So these are the types of colors that we see when we shine sunlight through a prism. And the way that we remember these colors, as you may see in a rainbow, is through the mnemonic Roy G. Biv. So that's a great way to remember it. These colors of light are actually considered as visible light. And visible light is actually one type of electromagnetic radiation. There's actually many types of wave radiation, and these include gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. So here I've listed the entire electromagnetic spectrum, starting from gamma rays to radio waves. And this is a symbol for wavelength, also known as lambda. You can see it as this symbol. For wavelengths, we measure it in nanometers, starting from less than 0.01 nanometer all the way to greater than 1 millimeter. So this is the entire range. Gamma rays, you should know, have the most frequency. So frequency, we define it as 1 over the period. So this is basically cycles, the number of cycles you have over time. You can also say that's revolutions over time. And the period is actually the inverse of frequency. So T equals 1 over F. You wouldn't really have to know this, but understanding the general concept may help you in astronomy. And from gamma rays, since we have the most frequency, we can expect the most energy. So we can say that frequency, as we increase the frequency, the energy, E, also increases. And the wavelength, lambda, actually decreases. So you would imagine something like this. So if we increase the frequency, it should look something like this. Pretend this is the X and Y axes. And we would have a lot of waves passing through the X axis. If frequency decreases, then we would have something that's more spread out like this. This would be a longer wavelength. Wavelength increases, frequency decreases. Always remember this relationship as it's very important. And also energy decreases. Sometimes we associate energy with temperature in astronomy and other sciences, so we can also say that sometimes temperature decreases. So we can say this associates with this graph, and this associates with this graph. Now we're going to be covering some of the anatomy of the wave. From this peak right here to the x-axis is called the amplitude, as we define it as A amplitude. So that's the amplitude. This is the crest as we know it, and this is the trough. Other than this, we're going to say and define lambda to be the distance from one crest or trough to the next. So this would just be something like this. If we have an x and y, we can see a wave that passes from here, goes down, goes back up. From here, this peak to this other peak is considered as a wavelength, or lambda. Now we're going to formally define frequency, and the way I like to define it is by doing frequency f is the number of times per second in which a crest passes some fixed plane Q. So by this definition, we mean that if we draw a wavelength like this, and that plane Q is right here, we see that there's two peaks right here, and if both of them passes through Q, then we would get a certain frequency. If multiple or many peaks pass through the plane Q, then the frequency will be higher. So this plane Q is actually defining our frequency. Now I'd like to go back to some of the equations that we mentioned before, such as 1 over f, 1 over t. Something new that we can add is the wavelength times the frequency is equal to the velocity. And that's also equal to the speed of light. As you remember, is 3 times 10 to the 5th kilometers per second. And this is an important equation because we're able to solve for a certain speed or a certain frequency defined by this constant. So one other equation that we can add to our arsenal is E equals hf. That gives us the energy of a photon. Always know that light can not only behave as waves, but it can also behave as discrete particles, and that's called a photon. So because we know that E equals hf and that lambda times frequency equals velocity, we can actually substitute frequency with c over lambda. So we can say that this, and then we just divide frequency equals c over lambda. And we just substitute and we get hc over lambda. Sometimes you may see this equation. One thing I forgot to mention is that visible light is divided into many colors, but these colors have a certain wavelength to them. And for example, red is usually around 680 nanometers. Orange is around 610 nanometers. Yellow, 580, and etc. So these have specific wavelength ranges that you had to attain in order for this color to appear. And note that visible light is the only part of the electromagnetic spectrum that we can see, and that's from 400 to 750. Because we can only detect a small range of all EM radiation, it's really critical for us to use other tools to detect other types of radiation. And one thing that we can address is that all electromagnetic radiation in a vacuum travels at the same speed, and that's the speed of light, c, regardless of the wavelength that it's traveling at. However, it does slow down in other types of mediums, such as glass or water. But overall, the measured speed of light is independent of the observer's speed, and that's usually the case. So the last point that I want to end off is that lots of photons with the same color make up the electromagnetic wave of wavelength lambda. and try to take this point to the next lesson that we will be addressing again with photons. Thank you.